Today's tutorial will be on how to write thermochemical equations. This is another tutorial in topic 5 on energetics and thermochemistry. Thermochemical equations are regular chemical equations that add the enthalpy of reaction. When we have a positive change in enthalpy, the change in enthalpy will be written on the reactant side. When we have a negative change in enthalpy or an exothermic reaction, the enthalpy of the reaction will be written on the product side. And since we're indicating whether the heat is going to be absorbed or released by the reaction, we do not need to include the charge of the enthalpy or the sign. So there are two different types of reactions that we're going to be writing equations for in this tutorial, and one of them is the standard enthalpy of formation. Remember, the enthalpy of formation describes, the equation describes the formation of 1 mole of a compound from its elements, and everything's at standard state, which is room temperature 293 Kelvin and 100 kilopascals, which is about sea level. These enthalpy of formation values can be found on page 12 of your data booklet. Remember, when we're writing these equations, we're going to be forming these compounds from the elements, and we need to remember that all the diatomic elements need to have a subscript of 2. Because we can't change the 1 mole of the substance, we might need to use fractional coefficients, which we've generally not used at all, and sometimes with oxygen. So you might be using a fractional coefficient with some of the diatomic elements. And then all the states of matter must be included in these thermochemical equations, just like they are in a normal equation. So let's do one sample problem. Write the equation for the formation of 1 mole of propane. So I turn in my data booklet to the 12, and I look for propane, and I see that the chemical equation for propane is C3, as I know, pro is a prefix for 3, C3H8, and this is a gas at room temperature. I also see that the delta H of formation value is negative 105 kilojoules per mole. So then I know that I'm going to be adding, the energy is going to be on the product side, it's going to be released. So I write 105, and I don't need the negative, kilojoules per mole. And this is per mole because by definition, enthalpies of formation are just 1 mole of that substance being formed. Now I go over onto the reactant side, and I see that I have carbon as one of my atoms, so I'm going to take 6 moles of carbon, which is solid at room temperature, and I need 8 moles of hydrogen, and hydrogen is one of my diatomic elements, and it's a gas at room temperature, and I'm going to need 4 moles of it, so I have 8. And so here's my thermochemical equation. The next kind of thermochemical equations that you'll need to write are on combustion. In this case, instead of producing 1 mole of a substance, I'm going to be burning 1 mole of the substance. So my reactants have to be my reactant that's going to be combusted has to be 1 mole. We're going to use section 13 of our data booklet to find these enthalpies of combustion. And we're always going to assume that the products are water and carbon dioxide unless otherwise notified. So the sample problem we're going to be using is for the combustion of 1 mole of octane. So I turned in my data booklet, and I discovered that the chemical formula for octane appropriately is C8H18. So let's get that in here, C8H18, and the data booklet also lets me know that this substance is liquid at room temperature, and I know I'm going to burn it in the presence of oxygen, which is a gas. My two products are going to be carbon dioxide, which is a gas at room temperature, and water. Notice how I've left room to balance this equation, and water is going to be liquid, not gas. And then I know that the enthalpy of combustion is negative 5,470 kilojoules per mole. So that means it's going to be released exothermic. So I'm going to write my energy value on the product side. So 5,470 kilojoules. I don't have to write the negative value because it's on the product side, meaning that the energy is going to be released. And since I'm burning 1 mole of the substance, I add the 1 mole to my units. All right, now I need to balance my equation, and I see that I have 8 carbons on the reactant side, so I need 8 carbons on this side. I have 18 hydrogens on my reactant side, so I need 18 hydrogens on this side. So now I have 9 oxygens here, and I have 16 oxygens there, so that gives me a total of 25 oxygens. So I'm going to just write 25, since this is an odd number, I'm going to write 25 half O2s, and that'll give me 25 oxygens. So that's the thermochemical equation for the standard enthalpy of combustion of 1 mole of octane. Got some more sample problems to work on, and the answer key is posted in Schoology under topic 5.